So we're beginning Unit 4 with this lecture, and Unit 4 covers Chapter 6. So let's get into 6.1, an introduction to polynomial functions. So we're going to start right off. I'm going to hit you with a whole bunch of polynomial function forms, and it's good to look at all of these together to get an idea of the pattern. And some of these we have definitely studied already. So for example, the first one, a first-degree polynomial function. We certainly know this. A first-degree polynomial function is also called a linear function, so that's not new for us. And it has the form f of x equals ax plus b. So a linear function is a kind of polynomial function. So the class of polynomial functions contains linear functions. First degree. So what does that mean? The first degree means, and it's a little, you don't really see it too much until you kind of go to second degree and third degree, but first degree is the power that the variable, to which the variable is raised. So in this case, this variable is actually raised to a power. That's raised to the power 1, right? So ax to the first power is really what we have here. It's just that the 1 doesn't change anything, so we tend not to write it. But that's why this is called a first degree polynomial. So if we go to the second degree polynomial, we have a couple of changes. The first thing that makes it a second degree is this. The power of the x variable is, the highest power is a 2. Not only that, but we kind of, you can almost sort of think of this as like, here's like the linear portion, like the bx plus c. We just kind of shift the letters over, and then we add a squared term to it. So we have like the linear plus the squared term. Now granted, the b and c, or the b is kind of now become the c, and the a is moved over to the b, and so on and so forth. But you know, these are just letters. So a second degree quadratic, or rather a secondary polynomial function, also known as a quadratic, ax squared plus bx plus c. Okay, very important. And this is the one that we're going to focus most of our attention on. Now we can keep going with this if we basically take the quadratic portion and then add a third degree term. We get the cubic, ax cubed plus bx squared plus cx plus d. And then if we take the whole cubic and we shift all the letters over and add a fourth degree term, we have what's called a quartic polynomial. So we have a bunch of terms in a quartic polynomial. By the way, just to remind you, the difference between a term and a factor, a term is something that's separated by a plus or a minus, and a factor is something that has a multiplication in it. So this is a, say in this quadratic we have 3 terms, and 2 of these terms have factors. So this factor is a times x squared and b times x. Terminology is kind of important here. Alright, so we could actually keep going with this as long as we wanted to, that we could have a 5th degree, 6th degree, and so on and so forth. And that always just means the highest power that's in the variable. And there's no end to this. You can have a polynomial of any degree that you want. Although we're not going to study them beyond the 4th degree. Alright, so what we're going to do now is going to drill down into the quadratic quite a bit more. So let's start with the standard form of a quadratic function. So the standard form of a quadratic function with leading coefficient a not equal to 0 is the following: f of x equals ax squared plus bx plus c. That's the same form that we were looking at just a moment ago. So the a not equal to 0 is simply because if a was equal to 0, then this term wouldn't be here. Because if a was 0, this would just cancel. And then you'd basically just have a linear function. So we don't want it to be linear. So that's why we have that restriction. If you graph this, you come up with this nice figure which basically it either looks like this or it looks like this, one of these two, and that's called a parabola. So this is an upwards parabola, this is a downwards facing parabola. The parabola has a single turning point, which is called the vertex. Briefly explained, this parabola is concave up, and here's the vertex right there. This parabola is concave down, and there's its vertex. So there's a lot of other little things that we can say about the domain and range and so forth, and we'll get into all that. But let's go ahead and look at an example first. Let's find the vertex on the graph of this quadratic right here. So let me pull up my calculator. First of all, let me give you a little, and I think that this is going to be in a slide in a moment, but I want to go ahead and mention that there's a nice property that if the leading coefficient is greater than 0, then it opens up the parabola. And if the leading coefficient, that's an A, is less than 0, it opens down. So we'll make this more official in a moment, but I just wanted to mention that because I know that since this is less than 0, that this parabola is going to look like this. And so the vertex will be a max in this case because it's opening downwards. If the parabola had been opening upwards, then the vertex would be a minimum. That's kind of useful for what we're going to do now. So the first thing I need to do is enter the function. Okay, and I am going to just use a square window for right now and do zoom fit. And we may need to mess with this if we don't see enough of what we want to see. So I know that, so you see here I've got this downwards opening parabola. I want to find the vertex, which I know is kind of up here in this area. I can't really see it very good though, so what I'd actually like to do is kind of zoom in on this portion of the graph. So basically I've got way too much stuff down here that I don't need at the moment, and I want to have more vertical headroom. So I could do this in a number of ways, but I'm just going to manually change my window from negative, and this is, I'm just sort of roughly picking out some values, negative 25 to 50. And I notice I only changed the Y values here. I didn't change anything but that. And that's just so I can more clearly see the vertex. There's many ways you could do this, but that's just a quick rough way of getting a better picture if I can see where I want to go. So I want to find the coordinates of this vertex. Now this is a maximum, so we actually have a function that allows us to find this. If you go to second trace or second calc, you see number 4 says maximum. That's what we're going to use here. And so to use the maximum function, the first thing that I want to do is it asks me for left bound. So that means move your cursor to the left of the vertex. So if the vertex I think is around here, my left bound is, anywhere over here. Hit enter. Then it's going to ask me for a right bound, so I'll move my vertex anywhere to the right of the vertex. And then it says take a guess, and that looks about right there. You can actually look at these numbers down here to see, but that looks pretty good. Then I'll hit enter a third time, and it's going to calculate my maximum to be, actually that's really 2.999987, so I'm going to call that 3, 37.5. And whoops, let me pause for a moment. Okay, so as I was saying, this is 3, 37.5. That's the coordinates of my maximum. Now, I wanted to go ahead and show you that, but there is another way to do this, as this slide says, algebraically. Actually, this slide has both methods. It has the method we just used, which is down here, but there's also an algebraic method. And it's important that you see this algebraic method, because if you go to pre-calculus or basically any other math class, you're probably going to be doing it this way. So, very briefly, algebraically, well, there's a formula for the vertex, and the formula is built by looking at the coefficients. These are the coefficients, A, B, and then C, and the x coordinate of the vertex is given by negative b over 2a, and the y coordinate of the vertex is, well, the function evaluated at the x coordinate. So in regards to this problem, let me pull up my whiteboard. Make a little more space here. Negative b over 2a is negative, and you have to be careful with the negatives because sometimes, you know, well, you have a double negative here. Negative 1.5, I'm sorry, whoops, negative 9, that's b, over 2a is negative 1.5. So this happens to be numbers that I can calculate. So that happens to be, you know, 2 times 1.5 is 3. But this is negative over negative, so that's positive. So this is 9 over 3, so that's 3. So this is saying that the x-coordinate is 3, and then f of 3 would be the function evaluated at 3. And so for that, I could just go to the calculator and do vars, y vars, because I already entered the function y1 of 3, and I get 37.5, which is exactly the point that we just found. So you can find this algebraically, or you can find it graphically. Either method is fine. This is really useful, the algebraic method, because, well, it's pretty fast, really, and you don't have to have a calculator. I mean, you might need a calculator to do your computations, but you don't have to have a graphing calculator to do it, which is nice. If you're going to use the graphical method, the one that we just looked at was, we use CalcMax, but notice that you can also very often, not can, but will need to use CalcMinimum if you have a negative leading coefficient. A is called, by the way, A is called the leading coefficient. Leading coefficient. If A is negative, we're going to have CalcMinimum because we will have a parabola opening up. If A is, I'm sorry, I think I just said negative. If A is positive, we will have an upwards opening parabola, and therefore we'll use CalcMinimum. If A is negative, we'll have a downwards opening parabola, and therefore we'll use CalcMax. That's what we just did. Okay. Okay, so you have multiple ways to do this. When we graphed the function, my graphing method was sort of loose. I just went with negative 10 to positive 10. This slide presents a slightly more organized way of going about that. Although when it says zoom standard, I think this uses a square box. Actually, I'm about to run out of time on this video, so we will pause this and return to this subject in the next video.